Are you ready to learn about the cutting-edge technology that could power our world for centuries to come? Join me as we dive into the exciting world of nuclear energy and discover the latest breakthroughs in fusion and fission reactors. Hello, and welcome to this video on the future of energy. We all know that energy is essential for our daily lives, but the way we produce it today is not sustainable. Fossil fuels are running out, and they are also causing irreversible damage to our planet. That's why scientists and engineers are working hard to find alternative sources of energy that are clean, safe, and reliable. And today, we will talk about one of the most promising sources of energy, nuclear power. Part 1. What are fusion and fission reactors? Let's start by understanding the difference between fusion and fission reactors. Fusion is the process of combining two atomic nuclei to form a heavier nucleus, releasing a tremendous amount of energy in the process. This is how the sun produces its energy. On the other hand, fission is the process of splitting a heavy atomic nucleus into smaller ones, also releasing a significant amount of energy. This is how nuclear power plants generate electricity. Fusion and fission reactions are both nuclear processes that release energy through the manipulation of atomic nuclei. In a fusion reaction, two light atomic nuclei combine to form a heavier nucleus, resulting in a release of energy. This energy is the result of the difference in mass between the reactants and the product. The mass of the product nucleus is less than the sum of the reactant nuclei, and this missing mass is converted into energy, as described by Einstein's famous equation, E=mc². Fusion reactions require extremely high temperatures and pressures to overcome the repulsive forces between atomic nuclei. In stars like the Sun, fusion occurs naturally as a result of the high temperature and pressure at their cores. On Earth, however, scientists have not yet been able to sustain a controlled fusion reaction for a prolonged period. Fusion research is conducted in experimental reactors that use powerful magnetic fields to contain and heat the plasma, allowing fusion to occur. Fission, on the other hand, involves the splitting of a heavy atomic nucleus into two or more smaller nuclei, releasing a large amount of energy in the process. Fission occurs spontaneously in some heavy nuclei, but it can also be induced by bombarding the nucleus with high-energy particles, such as neutrons. Nuclear power plants use the energy released by fission to heat water, producing steam that drives turbines to generate electricity. Unlike fusion, fission reactions can be sustained in a controlled manner in power plants. However, the radioactive waste produced by fission is highly dangerous and requires careful management and disposal. Fission reactors can also pose a risk of accidents, as demonstrated by incidents like the Chernobyl disaster in 1986 and the Fukushima Daiichi nuclear disaster in 2011. While fusion and fission reactors have some similarities in their basic principles, they have vastly different potentials for energy production. Fusion has the potential to produce vast amounts of energy with minimal waste and no greenhouse gas emissions, making it an attractive option for a sustainable energy source. Fission, on the other hand, is already a well-established technology that can provide reliable energy, but it has significant challenges in terms of safety and waste management. Part 2. Advantages and limitations of fusion and fission reactors. Now that we know what fusion and fission are, let's discuss their advantages and limitations. Fusion has the potential to produce almost unlimited amounts of energy, using abundant resources like hydrogen isotopes. Plus, it doesn't produce any greenhouse gases or radioactive waste. However, fusion technology is still in its early stages of development, and scientists are struggling to achieve a sustained and controlled fusion reaction. Meanwhile, fission reactors are already in use worldwide and can produce large amounts of energy with a relatively small amount of fuel. However, they produce radioactive waste that must be stored safely for thousands of years, and there is always a risk of a nuclear accident. Another advantage of fusion reactors is that they are inherently safe, with no risk of a runaway reaction or meltdown. If the magnetic fields containing the plasma fail, the reaction simply stops. Additionally, the fuel for fusion reactions is abundant and can be easily extracted from seawater, making it a potentially sustainable and cost-effective energy source in the long term. However, fusion reactors require significant upfront investment and technological development, and it may take decades before they become commercially viable. In contrast, fission reactors have been in use for over half a century and have a proven track record of producing reliable energy. They can also operate at a high capacity factor, meaning they can generate electricity consistently throughout the day. Fission reactors are also highly scalable, with reactors ranging from small modular designs to large power plants. However, the cost of building new fission reactors is high, and the risks associated with radioactive waste disposal and potential accidents must be carefully managed. Another limitation of fusion and fission reactors is their dependence on rare and expensive materials, such as lithium for fusion reactors and uranium for fission reactors. This dependence can create geopolitical and economic challenges, as countries with access to these resources can hold significant power in the global energy market. Research into alternative fuel sources for both fusion and fission reactors is ongoing, with some promising developments in thorium-based fission reactors and alternative fusion fuels. Furthermore, both fusion and fission reactors require significant public acceptance and trust to be widely adopted as sources of energy. Public concern over the risks of nuclear accidents and radioactive waste has led to significant opposition to nuclear energy in some countries. Education and transparent communication about the risks and benefits of nuclear energy will be crucial to building public trust and support for nuclear power. Part 3: Advances in Fusion and Fission Technology. Despite their limitations, both fusion and fission reactors have come a long way since their inception. In recent years, there have been significant breakthroughs in fusion technology, with experimental reactors like ITER showing promising results. On the other hand, fission technology has also evolved, with new designs of reactors that are safer, more efficient, and produce less waste. For example, molten salt reactors are a type of fission reactor that uses liquid fuel instead of solid fuel, making them more flexible and safer to operate. One of the major advances in fusion technology is the development of magnetic confinement fusion, which uses powerful magnetic fields to contain and stabilize the plasma required for fusion reactions. ITER, a collaborative project between 35 countries, is currently under construction and aims to achieve a sustained fusion reaction that produces more energy than it consumes. If successful, ITER could pave the way for the development of commercial fusion reactors. Another promising approach to fusion is inertial confinement fusion, which uses lasers to compress a small amount of fuel to create a fusion reaction. Research into both magnetic confinement and inertial confinement fusion is ongoing, with the potential to revolutionize the energy industry. In the field of fission reactors, there has been significant progress in developing small modular reactors, SMRs, which are smaller and more flexible than traditional nuclear power plants. SMRs can be used for a variety of applications, such as providing power to remote communities or as a backup power source for critical infrastructure. They also have lower capital costs and can be built in a factory setting, reducing the time and cost required to build a reactor. Another promising development is the use of thorium as a fuel for fission reactors. Thorium is more abundant and produces less radioactive waste than uranium, making it a potentially safer and more sustainable fuel source for nuclear energy. Advances in materials science and engineering have also improved the safety and efficiency of both fusion and fission reactors. For example, new materials like high-temperature superconductors can be used to create more powerful magnetic fields for fusion reactors, while advanced fuels and coolants can improve the performance of fission reactors. Additionally, digital technologies like artificial intelligence and machine learning can be used to optimize the performance of reactors and improve safety. Conclusion. In conclusion, the future of energy is nuclear, and fusion and fission reactors are at the forefront of this revolution. While there are still challenges to overcome, the progress made so far is impressive, and we can be optimistic about what's to come. Whether it's fusion, fission, or a combination of both, nuclear energy could provide a reliable and sustainable source of power for generations to come. Thank you for watching, and don't forget to subscribe to our channel for more exciting videos on science and technology.